We have to talk about some unusual metathesis reactions. These are still ion combinations, but they're a little tricky because the ions aren't so obvious. And so the next series of metathesis reactions we're talking about involve ammonia and the amine. Ammonia is NH3. Amines, these are a class of organic compounds that look like ammonia and behave like ammonia. And so these are given the formula NR3, where R is equal to hydrogen and or carbon. If we look at the Lewis structures for ammonia, what's one chemical property that you know for ammonia? One chemical property of ammonia. It's combustible. Yeah, this is one of the redox properties. It's combustible. It will form some toxic gases on combustion. Watch out for it. You don't want to burn ammonia. It is combustible. This is a redox. Anything else you know about ammonia? One of the properties that we're going to look at is it's a weak base. Ammonia is a weak base. So what makes it a weak base? What makes it a weak base is that it's a proton acceptor. You know, ammonia will accept a proton. Proton is positively charged. What about ammonia? You know, where does that proton? It's going to go on the nitrogen. If you look at the oxidation state of nitrogen, what is it? The oxidation state of nitrogen. This is why it's combustible also. Oxidation state's winner take all. The electrons. How many valence electrons does nitrogen have? Nitrogen has 5 valence electrons. How many electrons does it have here? 8. 3 extra electrons, minus 3. And so its oxidation state is minus 3, making it electron rich. Well, the electron rich also makes it basic. Because basic compounds need to attract protons. Protons are positive. This is just electrical interactions. And so this is a weak base. Let's compare that with simple amine. Simple amine might be something like this. This is methylamine. Methylamine is also a weak base. The reason it's a weak base as well is because the nitrogen, the negative charge density on nitrogen didn't really change much. Because if we look at the electronegativity of hydrogen, do you know the electronegativity? Probably not, but the electronegativity is, which I'll call EN, is 2.1. Versus the electronegativity of carbon is 2.5 or 2.4. 2.5, 2.4, one of those. Are those two electronegativities close to each other, or are they far apart from each other? What do you think? Are those comparable electronegativities, or quite different? This is a lot of people don't bother learning numbers. They don't bother learning numbers, but the people who don't bother learning any numbers get asked questions with numbers are going to have a hard time. And so the numbers that you learn is, you know, how far do these electronegativities span? What's the range, you know, electronegativities? The range of electronegativities is like 0.7 to 4, which doesn't seem like a huge one. The other thing is, it's learning about, you know, something about these numbers. For example, 2.5 and 2.1, what we call comparable electronegativities. Those electronegativities are very close to each other. In fact, the difference, some people say, is negligible. There is a difference. You know, carbon's more electronegative than hydrogen. But a lot of people say that the difference is negligible, and therefore hydrocarbons, you ever heard of hydrocarbons, or just compounds of carbon and hydrogen, no matter how complex their structure is, will always be non-polar. They're always going to be non-polar because there's no difference really, or not much difference in the electronegativities of the elements. And so when we look at this is called a methyl group here. This is fairly non-polar, and all the bonds are pretty symmetric. Whereas carbon and nitrogen is polar, and nitrogen and hydrogen is a very polar bond. You guys remember about bond polarities? Yeah. And so that's it. And so if we have a hydrogen here, well, it's got some pull. If we have carbon, it just has a slightly greater pull, but still the negative charge density or the electron density on nitrogen should be about the same. And so the strength of these are about the same. You know, this one has a big bulky group attached here, and that could hinder reaction. This is called steric hindrance when we have physical blockage or potential blockage of reactants. But otherwise, the same kind of deal. Well, what do we know about weak bases? Tell me an electrolyte. What are the electrolyte properties of a weak base? It's a weak electrolyte. And weak electrolytes do what? Both of these are weak electrolytes. Weak electrolytes, we say partially dissociate, or ionize. Ionize is just break up into ions. You know, it's not like stripping electrons. It's not like a redox reaction. Partially dissociate or ionize. Right. And so let me give you a side example here. You know fluoride is a weak base? Fluoride? It's on the chart up here. Actually over here. Chloride is actually a weak base, but chloride is so weak we call it neutral. You know, like sodium chloride. If you have, let's say, an upset stomach or something, and you ran out of milk and magnesia, would you eat sodium chloride? Yeah, the chloride is too weak of a base. It's not going to do anything for you. And so chloride, even though it's up here, is so weak that its basic properties aren't significant. But fluoride's way down here, so fluoride's base properties are much more significant. Fluoride's a weak base. And so what does fluoride partially dissociate or ionize into? How can we break it up? In other words, into what ions would you ionize fluoride into? Well, it turns out that this is wrong. It's weak bases. Weak bases don't ionize or dissociate. Weak bases do this. They partially hydrolyze. You know, hydrolysis is this reaction with water, and so weak bases will partially hydrolyze. And so let me give you an example of that. So ammonia itself isn't going to split apart into ions. What is going to happen is ammonia is going to react with water and hydrolyze. And so bases are proton acceptors, so we accept a proton here. We're going to form ammonium and hydroxide. Since they're weak, the reverse reaction is more favored in this instance. I already said ammonium hydroxide is not so stable, but nonetheless, we can have collisions and create some ammonium and hydroxide. The major species are going to be ammonia and water. The minor species would be ammonium and hydroxide. Same thing, I mean, if we have methylamine, just the compound over there, methylamine is CH3NH2. This will partially hydrolyze water. In this case, base is a proton acceptor, so this accepts a proton and its positive charge, which gives us CH3, NH. We go from 2 to 3, so we add an extra hydrogen and a charge. And so we form the methyl ammonium ion. Methyl ammonium looks very similar to ammonium, it has 4 bonds to nitrogen and hydroxide. Methyl ammonium and hydroxide. Well, when we have weak bases in water, then we have the potential of generating some ions. Since we have the potential for generating some ions, those ions can react in a metathesis. Metathesis reactions are just ion combinations, right? And so let's see the react. We'll give an example here. We'll do magnesium. We'll do magnesium nitrate plus NH3 AQ. So both of these are aqueous. And then we got to figure out what's going to form here. Although this doesn't look like a double replacement reaction, does it? But it is. You know, this is a metathesis reaction. So how do we deal with something like this? Well, this is what we have to recognize. We have ammonia and there's water present. And so the ammonia plus the water yields what? Ammonium ions and hydroxide ions. And these ammonium ions and hydroxide ions can react. And so essentially, when we see this, we think ammonium hydroxide. And so here's our AB plus CD. So we get magnesium with hydroxide and ammonium with nitrate. And so what we should form here is magnesium with hydroxide yields MgOH2, and ammonium with nitrate just is NH4NO3. Then we look for driving force. Is there a driving force present? Well, magnesium hydroxide, most hydroxides are insoluble. So magnesium hydroxide is not one of the exceptions. And then we'll form this balance. We'll need 2 ammonium hydroxides here. And so we'll need 2 ammonias, 2 waters, form 2 ammonium hydroxides. And it's balanced. And so the driving force here is precipitation. Ammonium nitrate is not a gas former. And so let's rewrite this. So I want to write the complete equation. When I write the complete equation, I'll have magnesium nitrate plus, now what should I write here? Should I write this, 2 ammonium hydroxides? Or should I write this, 2 ammonias and 2 waters? Which one should I write? So for example, if I write 2 ammonium hydroxides then that yields magnesium hydroxide and 2 ammonium nitrate. Or should I write 2 ammonias and 2 waters? I should write 2 ammonias and 2 waters. Do you know why? Ammonium hydroxide is not that stable. It decomposes. But a little bit's formed when ammonia and water react. And so if you went to the chemical store and tried to buy a bottle of ammonium hydroxide, you're going to be disappointed because by the time you get home, you'll realize, oh, wait, it's ammonia and water, not ammonium hydroxide, mostly. And so will you be disappointed? No, because you should have known that. And the person who sold it to you probably figured that you're after ammonia and water, aqueous ammonia. And so when you go to buy the chemical, you'll buy aqueous ammonia. Aqueous ammonia, well, ammonia is a weak acid, and so it'll react with a little bit of water to form a little bit of ammonium ions and hydroxide ions, which in turn can react in a metathesis reaction. And so we don't write ammonium hydroxide here because that's not the bottle of reagent that you're going to grab off the shelf. The bottle of reagent you're going to grab off the shelf is ammonium. This is going to yield magnesium hydroxide, or driving force, solid formation, and 2 ammonium nitrates, which are aqueous. Well, we can do the ionic equation for this and the net ionic equation also. The ionic equation, magnesium nitrate, is that a strong acid? No. Is it a strong base? No. But it is a soluble salt. So this is going to dissociate into magnesium 2+ and 2 nitrates. You have to be careful because a lot of people will write 1 nitrate. No, don't balance it. It has to be 2 nitrates for every magnesium. And then we go to ammonia. Is ammonia a strong acid? No. Strong base? No. Soluble salt? No. If it's neither of those, we just leave it alone. It's 2 ammonias. Water, the same thing. It's not a strong acid, strong base, or soluble salt. Magnesium hydroxide. Magnesium hydroxide is a salt, but it's an insoluble salt. So insoluble salts we just leave as is. And then ammonium nitrate, well, that's a soluble salt. That's going to go to 2 ammoniums plus a nitrate. Well, this is a common mistake because this is not balanced. Do you see? If I have 2 ammonium nitrates, how many nitrates do I end up with? 2. And so to properly balance this, I need to write 2 here. And so the driving force, like I said, we only need 1 driving force in this, and that was the precipitation here. Earlier. Well, the net ionic equation is going to eliminate the spectator, so looks like nitrate doesn't change. How about ammonia? Well, ammonia is a base. Ammonium is an acid, so these 2 are different species, and so we can't cancel them out. So we'll get rid of the nitrates because that's the same on both sides. So magnesium ion plus 2 ammonia plus 2 water yields magnesium hydroxide solid plus 2 nitrates. Okay, we got to make sure it balances out. You know, the charge and the atoms must balance. But yeah, this one, obviously the charges aren't balanced because it's positively charged on the left. This is negatively charged on the right. So I screwed this up. It should be, sorry, 2 ammoniums, not 2 nitrates. Okay, now the charges and the atoms should balance. That's a metathesis reaction with aqueous ammonia. For the amines, it's the same type of deal, you know. I'm gonna do this. I'm gonna do it with an amine instead. let's make it like this. Do you know what we call this amine? You know what a CH3 is called? Methyl. And so this is called trimethylamine. Trimethylamine. With trimethylamine, you just imagine the carbon and hydrogen is kind of interchangeable based on electronegativity. And so having carbon here or hydrogen here doesn't really change the nitrogen's electronic environment significantly. This is a very, very minor change. There's a very minor difference in basicity. But the same thing, you know, this is going to hydrolyze water to form what? Well, water reacts with this, you know, weak bases. Water's amphoteric. Basically, this nitrogen is going to collide with the hydrogen here and knock it off, give us some hydroxide. So we end up with this. We end up with, I'm going to condense these. These are condensed structural formulas rather than expanding it out. We'll just call it CH3. This is called the trimethyl ammonium ion. Trimethyl ammonium and hydroxide. I'm going to get rid of the brackets this time. And so it's the same thing. If there's magnesium present, magnesium likes hydroxide, iron likes hydroxide, aluminum likes hydroxide. So we could do an example here. We'll just do aluminum chloride plus this, CH3N. CH3,3N yields what? Well, you have to recognize this is a amine. This being an amine, we treat CH3N as if it were this. What we do is we add an H2O liquid. After we add the H2O liquid, then it's going to form CH3,3NH plus OH minus. So we treat it as trimethyl trimethyl ammonium hydroxide. And we switch the ions. And so what we should form is aluminum hydroxide and this trimethyl ammonium with the cation. And the anion would be chloride, so we form trimethyl ammonium chloride. Yeah. Do we have a driving force? We have a driving force. The driving force is the precipitation of aluminum hydroxide. This should precipitate. This is a driving force. We need 3 hydroxides, so we'll need 3 of these. So we'll get 3, 3, 3, and 3. It should give us 3 trimethyl ammonium chlorides. So let's rewrite this as the complete equation here. Rewriting this as a complete equation, I get aluminum chloride plus 3 trimethyl amines or ammonium chloride, or ammonium hydroxide. Amine plus 3 H2O liquids is going to give us aluminum hydroxide solid plus 3 trimethyl ammonium chlorides. We'll go to the ionic equation. Aluminum chloride, is that a strong acid, strong base, or a soluble salt? It's a soluble salt, so we split it up or ionize it. Al3 plus 3 chlorides. Trimethylamine, strong acid, strong base, soluble salt? No, neither. So we leave that alone. Water, neither of those. Aluminum hydroxide is insoluble, so we don't do anything. Trimethyl ammonium chloride. Strong acid, strong base, soluble salt? Soluble salt. And so what does this lead? This is going to give us 3 trimethyl ammonium ions plus 3 chloride ions. We get rid of the spectators. It looks like chloride is a spectator. And so the NIE will just be aluminum 3 plus 3 trimethyl amines plus 3 H2O liquids yield aluminum hydroxide solid plus 3 trimethyl ammonium ions. That should be it. All right, we're out of time here, so those are the examples.
What's the cutoff for chapter 5?
Actually, you know what, I decided, because I went out of order. Normally when I do chapter 5, I do electrolyte properties first. I skipped those. And so no chapter 5 on your test. Yeah, could you bring a Scantron? You know, the skinny ones, long skinny one. Scantron. You'll have the whole period to do the test tomorrow. You aren't doing any reactions tomorrow. You don't have to predict. You'll just have nomenclature, that kind of stuff. No chapter 5. The past exam I posted on Piazza had chapter 5 in there. You could ignore that chapter 5 stuff. I've just decided to keep it cleaner. This format's going to be very similar to that one. People were asking me about the key. You know, I'm not going to post the key to this. If you have questions about it, you can write you know, your questions on Piazza. I'll answer those. But it's going to be like an exam. On an exam, you don't have your book. It's not an open book, but this take-home, you can just open your book and then see. So you want to kind of get some confidence. But nonetheless, if you have questions about specific problems, post it on Piazza and then see, you know, what other people got. And if you show me how your thinking was, then I'll correct it if it's wrong. Okay.